So all that boundary stuff was just a preamble to get us to Stokes' theorem. So this is a statement of Stokes' theorem, and there are a lot of conditions that go into this theorem, and I'm not going to spend a lot of time paying attention to a lot of these. Stokes' theorem says, assume that S is an oriented, piecewise smooth surface. So what does that mean? Oriented means that it has some normal vector, and we know about normal vectors. Piecewise smooth just means that it's a nice smooth surface and that you don't have gaps. And we aren't going to worry too much about that. There's also a one-to-one condition with its parameterization that I'm not going to worry about either. And we're going to have this surface bounded by a closed curve or a finite union of closed curves. So like we saw with the cylinder, the cylinder had two different boundary circles, right? But each of those circles were closed curves, and there's a finite number of them. In this case, there were just two. Next, we'll let this notation, my ds, is going to be the boundary of S. Again, I hate this notation, but this is standard notation. This is our boundary of S. Just like with our cylinder, it was the top circle and the bottom circle. And the boundary has to have positive orientation, which is what we just talked about. Finally, we're going to let F be a vector field in R3, and that vector field is going to have continuous partial derivatives, so that we can take partials and our curl works out okay. Conclusion. With all those caveats, we get to the fact that our line integral of F over the boundary is exactly equal to our surface integral, our vector surface integral, over the curl of F. That's our big conclusion, which is a really cool big conclusion. There are a couple of things that I want to point out. One is, let's write out in longhand. I'm going to erase all this top stuff. Let's write out in longhand what each of these pieces actually mean. So this left-hand side, this is talking about, it's a single integral, and it's over this boundary, which is a line. So we're saying that the vector line integral of our vector field F over our line, in this case our parameterized path given by the boundary of S, which has to be closed, that's what the circle is telling us, is going to be exactly equal to our vector surface integral of, is it of F? Because we want it to be F, and you're going to want to do that every single time, and it's not. And so maybe this is something that I'll highlight in red, that in order for Stokes' theorem to work, it's exactly like Green's theorem, the fact that it's not of F, it's of the curl of F. So the curl of F over the surface, where our surface S is given by S over the surface S. So I've already mentioned it. No, before I mention that, so these are the notations. This is our generic way of talking about it, but this isn't actually how we compute it. So let's recall, how do we compute vector line integrals? These are our formulas. Formula. When actually computing this, we need some pieces to be able to compute it. We're going to parameterize our boundary as a function of t, and so typically we're going to call this as an integral as t goes from a to b of f of, in this case, I'm going to let my boundary of S be parameterized by some function c of t. This is a function c of t. So this is f of c of t. And how do we compute our line integral? We have to dot it with c prime of t dt. Recall, this is parameterized in terms of length. In order to parameterize it in terms of time, I need to compute this dot product. So this is my formula for computing this vector line integral of f over the boundary of S. And what's our formula for being able to compute vector surface integrals? Recall that we're going to have to parameterize it in terms of both u and v. And I don't really care what the bounds on u and v are. Sometimes they're functions, sometimes not. But it's going to be the curl of f of careful, phi of uv parameterization of our surface dotted with our normal vector uv d v d u. I think that's all on camera. So when we calculate this, we're going to compute the curl of f, and then once you've computed the curl of f, you need to plug in what your u's and v's look like for your phi function. I want to compare this quickly. These are just our formulas for how to compute each of these pieces. Let's compare this to Green's theorem. I'll write Green's theorem in green. Green's theorem, how very clever of me. Recall that Green's theorem actually had the exact same thing. It did the exact same thing, only for R2. It turns out that Green's theorem is exactly the two-dimensional analog of Stokes' theorem. That Stokes' theorem only applies to vectors in R3 and surfaces that are up in R3, whereas Green's theorem applied to regions that were in R2 and surfaces and vector fields that were in R2. Because the statement of Green's theorem really is exactly the same thing. That the statement of Green's theorem says that I'm going to take the line integral over my function of f dot ds of the boundary of my region D, I think call my regions D, is going to be exactly equal to the double integral over that region D of the scalar curl of f dot ds, where our scalar curl, recall, was given by dq dx minus dp dy. You can see why this is exactly similar to our curl here. So I want to say that Stokes' theorem isn't really anything new. It's exactly the same thing as Green's theorem, but two different people discovered them, and so they have their separate theorems. That Green's theorem is sort of the baby version that's in R2, whereas Stokes' theorem is the bigger version that's in R3. And instead of dealing with flat regions, which is all that Green's theorem can do, we now can look at three-dimensional surfaces and three-dimensional vector fields. So what are some of the geometric implications of this? I'll do one quick picture. And essentially this is saying, my picture is telling me, let's say that I have some surface. This is going to be a weird surface, and the boundary I'll draw in green. It's going to have this open boundary down here at the bottom. And I have to think to myself, if I have an outward pointing normal vector, this is my normal vector pointing out, and my turtle is going to walk, I need to make sure that I keep the region on the left for my turtle. So drawing my turtle. Uh-oh, too many legs on the turtle. The region has to be on the left of the turtle, so it means that I'm going to orient this boundary this way. Regardless, let's say that this is my surface. It's saying that if I wanted to compute this line integral, and it was some crazy surface, and computing the line integral was difficult, instead of computing the line integral, I could compute the double integral over the surface, where I'm using the curl of f as my function, my interior function that I'm integrating over. But notice that any function that has the same boundary, it means that this double integral is going to come out the same. In particular, let's say that I just had a cone with the same boundary, or maybe I had just the disk, right? Like a flat disk. If that was my surface, all of them share the same boundary, which means that all of these integrals would be the same no matter what, which means that the double integral over the curl of f for all of those different surfaces is always going to give me the same value. So if I wanted to, I could pick the easiest surface that I wanted that still shared with this common boundary, and that would give me the same result. And this is something that I'm going to write down as a theorem. Your book has it listed as a theorem, I believe. So this theorem is called the surface independence for curl vector fields theorem. And it says that we're setting up some notation. We're going to let f equal the curl of A. I don't know if I like this notation, but I'm consistent with the book. Then the flux of f, so the flux, recall, that's just the vector surface integral. Another word for that is flux. It's how much fluid is flowing through this surface given by the vector field. It's this double integral. So the flux of F through a surface S depends only on the oriented boundary, this boundary, and ds, and not on the surface. And that's this written exactly algebraically. It's exactly just a restatement of Stokes' theorem. It's just saying that no matter what surface I choose, the integral that's computing the flux over that surface can be defined just by this oriented boundary, which is exactly what we have. In particular, and this is an interesting side point, that if S is closed, so recall we had our closed surface that was a sphere. Anything that doesn't have any holes to be able to get from the inside to the outside, it doesn't have to be exactly a sphere. Even a rectangular box, something like this where it had all of its sides, right? There wouldn't be any boundary because there's no way to get from the inside to the outside of that surface. There are no holes. So if S is closed, then we know that this double integral over F, where F is equal to the curl of A, is going to be equal to 0, which is a cool result because we know that this is going to be exactly equal to the oriented line integral, vector line integral, over A ds. And if our boundary doesn't exist, then this boundary is just going to be 0, which gives that this is 0. And so computing the flux over this shape is also going to give us a 0 value.